frees up memory, but this I/O consumes memory bandwidth and valuable CPU time. Compacting is good for the memory, but at the cost of the CPU utilization. Okay, any questions?
Hocam bilmiyorum mantıklı bir sorum ama şurada bir memori vardı, bir de en üstü vardı. Bir kısmını oraya yükleyip kalan kısmını yukarıdan sonrasını yazması öyle bir şey mümkün değil mi hocam?
Not with the swapping method. If you are using paging, yes, maybe. We didn't talk about paging yet. And I mean, there are techniques that can do that. In this case, I am abstracting the memory only using a base and limit registers. You can say that. I mean, I cannot divide this process into more than one page with this mechanism. But if I use paging, which we will be talking about next week, I can do that. In that case, I don't need much compacting or relocation. Okay. So let's. Wow, what? Benim bu zamanım kim çalıyor ya? Ben ne yapıyorum ya? Ben aynı şeyleri mi tekrarlıyorum dersin ortasında bir yerde de 20 dakika gidiyor bir yerlere zaman ya. Okay. How much memory should be allocated for a process? Okay. So that's a good question. I mean, the obvious answer is if the process A, okay, it needs 100 Ks of data and it needs 200 Ks of instruction space. That means that I should allocate 300 kilobytes of memory location for the process A, but it is not that simple because remember the C programs, they can use malloc, right? They can allocate some space, dynamic allocation. They can do some allocation. That's why when you calculate this one, 100K for the data and 200K for the instruction space, then add more space so that the process A has more room for expansion. It's like that. Okay. So actually in use, I allocated a little bit more space, so there is a room for allocation. Okay, some space and there is room for allocation. Okay. When I do the swapping, when I am loading the processes back to the memory, you don't allocate exact memory that is needed for process A or B. You allocate a little bit more so that they have more room for growth. Okay, when they do the memory allocation. Okay, so that's something you need to. That's something that you need to consider. Even if this space is not enough for this process A, then you need to relocate the whole process to some other place in the memory. Maybe you need to write this to the disk, and load them again so that they have more space. So swapping can be used for allocating and relocating purposes. Sometimes, typically, this is my C program. My instructions are here, okay? My instructions are here. My heap is here, dynamic memory location here, and my stack is here. Stack grows downwards, okay? Bottom of the stack is here, and stack grows this way. And my dynamically allocated memory is using this way, okay? So, and this is the space that I allocated so that I would use them for the dynamic allocation and stack growth. Okay? So you don't allocate exactly what is needed. You allocate a little bit more. How much more? That's an operating system design issue. Maybe you could get data from the history, right? You run that process many times. You know how many times it needed the dynamic memory. Okay, you know how many times it needed dynamic memory. You can use that data to allocate space when you are loading a program. For your homework, you don't have this problem because in your with our structure, our operating system is so simple. We have only two calls. One is fork, one is the print, right? We don't have any dynamic memory allocation, so we don't have these problems. Maybe next homework I can introduce that, but I am not sure. So you are going to allocate exactly what the process needs with your operating system and the CPU. Okay, any questions about the swapping and the amount of memory location needed? Any questions? Then I will continue then. Okay, I will continue. If I have more than one process in my memory, usually I have this kind of space. There is some space for the operating system, some space for this process A, some for B, some places are empty, right? Like this one. Okay, occupied, empty, occupied, and empty. I should keep some kind of a data structure that keeps this information. What parts are occupied and what parts are empty, so that when a new process is loaded to the memory, I would know which part I should choose. That's a memory management issue. When memory is assigned dynamically, operating system must manage it. In general terms, there are two ways to keep track of memory usage. Okay, I need to know what parts of the memory is being used and what are not. There are two methods. One is the bitmap method. Okay, I have a bitmap table like that. Okay, each bit represents some amount of memory. Let's say this is 3K of memory, and these are allocation units, 3K. So this bit says that this 3K is occupied, this one is occupied, this one is occupied. So there are 5 ones because these five of them are occupied. Then there are zeros, these are not occupied. Then there are ones. Okay, so this is called memory management with bitmaps. Memory management with bitmaps. So each bit represents the allocation unit. If it is occupied, it is 1. If it is not occupied, it is 0. Okay. So when you are loading a new program, you come to this bitmap and you look for large enough space, maybe this part. Okay, I have 3 zeros, consecutive zeros. Each one is a 3K. So I have here, this place can hold 9 kilobytes of process space. If it is enough, then I would load my program here. If it is not enough, then I have to continue look for larger space. So this technique is called memory management with bitmaps. The other one, the alternative is that don't use the bitmaps, but use a linked list. Okay, it says that there is a process at address 0, and it uses 5 allocation units. 1, 2, 3, 4, 5. Okay, so this place corresponds to this one. And this is a linked list. Then there is a hole, there is an available place, and it is here. It starts at address 5, and there are 3 allocation units. Okay, then there is a process here, and there is a process there, and there is a hole here. You understand? Okay, so this is the second method, linked list method. It keeps a linked list of available memory locations and the occupied memory locations. When you need some space, then you just traverse this linked list, find large enough position, and you load your program in that position. Okay, next week we will continue from this part and continue with the other memory abstraction mechanisms. Any questions? Hadi o zaman.